say here is that when you are looking at the standard deviation, okay, when you're looking at the standard deviation, do I have the formula on this one or this other one? Okay, we can call it SD. You'll also see it as a little s. I have that anywhere. Okay. Big numbers mean that that data is more spread out. So here, okay, here is an example. One standard deviation, this means that 34% of the data that you collected is lower than the mean, and 34% is higher than the mean. So the bulk of it, 68% of your data is within one standard deviation. Okay? Two standard deviations mean that even more of your data is somewhere in that range. So when you did that practice problem, what was one standard deviation? What did you guys get for one standard? What were the numbers? It was 80. Let me break it down.
The mean was 84.
Okay, the mean was 80. Okay, so here was the mean. That's like the, I don't want to say middle because, you know, that's more like a mode or the median, I mean. But, you know, this is the average. Okay, so what was the standard deviation? 8.67? Okay, so what that means here is that, and I'm just using this as a side example, that's why I wanted you to go through it. What is 84 plus 8.67? This is one standard deviation. What is that value? 92.67. Okay. What is one standard deviation lower? What is 84 minus that number? 84 minus 8.67. You sounded hesitant. Is that what?
Yeah, 75.33.
Okay, so I'm going to get rid of this 8.67 now that we calculated it. Got it? Do you guys, do these numbers make sense? All I did is I took one of those values, you calculated it, and added it to the mean. Okay? I took that same value and subtracted it, so now I have a range. Okay, that's a range. So now I have a range that goes from 75.33 to 92.67. Does that make sense?
Yes.
Okay, looking at this, remember, 68% of your data, so like, what, is that like 2/3 kind of? That's close to 2/3, right? 68%? 60, okay. So 2/3 of your numbers, of your values, of your data will be within that range, 2/3. I'm gonna put like 2/3, just so we can eyeball it, okay? So 2/3 of our values, that's what this is saying, 2/3 of our values of X should be between 75.33 and 92.67. So look at them. Is 96 between these two values? Let me put it down. Look, these are our X values that was on the practice problems. See? Is 96 between 75.33 and 92.67?
No.
Is 88?
Yes.
Is 86?
Yes.
Is 84?
Yes.
Is 80?
Yes.
Is 70?
No.
So 4 out of 6 equals 2/3. So it shows us the range that the bulk of our data falls in. That's what standard deviation does, okay? The standard deviation, it shows us bulk of actual data falls in. here and I knew I wasn't gonna fit it in. I wanna draw a picture. Okay. Let's say our data was, let's say instead of 8.67, okay? Let's say our data, or our standard deviation was, let's just say 3 to make life easier, okay? 3. You cool with that? I'm making that number up. Let's say standard deviation is 3. If that's the case, what would one standard deviation added to 84 be?
87.
Yep, 87. So this is our fictitious. The red is just, I'm making it up, okay? What would 84 minus that standard deviation be?
81.
Is this range bigger or smaller?
Smaller.
Smaller. So, another thing you can tell from standard deviation, and I should have hit freeze. Let me go back in so I can freeze it. Is that how close to the median these numbers are clustered. The larger the standard deviation, the more spread out your data is. Okay? So we have larger standard deviation. Okay, we can still have the same number of data points. We can still have 6. But if the number is smaller, they're going to be more clustered together around, there's going to be more values that fall by the mean. Or they're going to be closer together, I should say. Okay? We like standard deviations. Do you think we'd prefer standard deviations to be small or big?
Small.
Yes. Okay, so you remember, did you guys learn the difference between precision and accuracy? No? Okay. Bullseye. Okay? I throw a dart. By the way, if I actually threw a dart at a dartboard, I would not get on the dartboard, but whatever. Okay, if I throw a dart 5 times, 1, 2, 3, 4, 5. Okay, did this hit the target?
No.
Is it accurate?
Yes. No.
No, it's not accurate because I didn't hit it. But am I precise?
Yeah.
Meaning that each time I threw it, I probably threw it the same way, right?
Uh-huh.
Okay. On the flip side, you have the same target. Okay. Closer to the bullseye if you were to average them all together.
Yeah.
Okay. Am I precise? Are all of them about the same spot?
No.
Yeah. So when we're using those terms, just letting you know, it doesn't necessarily mean bad and good. I mean, ideally you want to be accurate and precise, right? That would be an ideal situation, like all 5 of them right there at that bullseye. But sometimes that doesn't happen. Standard deviation cannot tell us necessarily how accurate it is, but it's telling us how precise. So the smaller the standard deviation, the more precise our measurements. Less variation. I don't know if I'm spelling precise right or not. Okay, less variation. The formula, you guys realize just calculating 6 values is tedious, okay? We will mostly use sheets to calculate it. Whenever we have data, a bunch of data, and we need to calculate it, there's this handy little dandy formula you can put into a box at the bottom. Have you guys used formula in Google Sheets or Excel? It will just calculate it for us, okay? I will not make you plug and chug all of those. Questions on this? So if we had done, just going back to our example here, if we had done 2 standard deviations and we had added another, was it 8.67, guys? What did we say that's standard deviation? It was
Yeah.
867?
Yeah.
Okay, so if we had added 2 standard deviations to that number, so we added another 8.67, that's like 101 point something, right? I don't know, I'm doing it in my head. So 101 point something or another. And if I had subtracted another one, so I'm now this is plus 2 SD, okay? Because I added one standard deviation and added it again. And I do the same backwards, which I can't do subtraction. Can you, someone tell me what 75.33 minus 8 is? Minus 9? Would that be,
Minus 9 is 66.33.
So it's gonna be about 66,
Yeah.
somewhere around there, 66 point something, how's that? So if we had subtracted 2 SD, we would now have a range from 66 to 101. Okay, 95% of our data will fall within 2 standard deviations. 1 standard deviation is 68% of our data. 2 standard deviations is 95% of our data. And look, all of our data is going to fall within that range. We didn't have many number values, so 95% is basically 100% when you're only looking at 6 values. Questions on that? Yeah.
Was it always a 68%?
Yes. 1 standard deviation. So this part right here, what I would tell you guys to highlight, if you want to highlight, this right here is perfect. 60, and if you want to put like 68% instead of the 34. And the same thing here, 2 standard deviations. Let's do this. Oh, that's what the cloud's for. That's why you put the cloud there. 68%, 95% will be in 2 standard deviations.
Always, like no matter what data we have?
Yes. Yep. Okay, so that is something that's important in that it shows the range. Bulk of actual data falls. Oh, it shows the range that the bulk of the data falls in. That's what this does. Okay? We can see where most of it falls. It's good for seeing how varied our data is. Okay? Measures variation. And if you want to do a visual, when that number is small, that means it's going to be closer to the median. All the values will be closer to the median or mean. And if it's large, they're going to be more varied. Okay? Further apart from each other. Did I lose you guys?
No. Well, not
Do
me.
you think thinking about those numbers and calculations and the data set, that practice problem, is it helping you guys? Okay, really quickly, because I'm going to have you guys calculate the standard deviation. There is another sheet, you guys are going to see that, but just an overview of SEM, standard error of the mean. It oftentimes goes hand in hand with standard deviation, and you guys probably noticed it because the formula actually involves calculating the standard deviation first, doesn't it?
Mm-hmm.
Okay, so SEM stands for standard error of the mean. This is where our accuracy comes into play. So think of this as kind of like a measure of our precision, and this is more the measure of that accuracy. And that's why we use it. This is where those error bars are going to come into play. This is a big SEM. So here with standard deviation, we won't plot that necessarily on a graph, okay? It's just a number value, but we can just glance at that number and kind of get an idea. But then once we plug it into a standard error of the mean, it gives us something that we can visualize. We can plot. So when we're looking at it, we can make inferences when we're looking at a graph. Okay? Small SEM, more precise. Now what it's doing, more accurate and precise. Let's do that. So we want this, okay? The next thing is about overlapping, but I don't even care about that right now. The dot is your mean. So this is saying, it's kind of like, think of it as almost like a standard deviation, but standard error of the mean will tell you, like adding and subtracting from the mean, your data is going to fall. So when you are doing raw data, when I say raw data, does that make sense? Where you plot every single point? Raw data, when you plot every single point, okay, and you were to look at it on a graph, you can kind of see that standard deviation. You can kind of see that bell curve look to it. But do you usually plot raw data on a graph? Like every single point? What do you usually plot, the average or the raw data?
The average.
That's when this is going to come into play. Okay, so now we'll just plot the average. We won't plot every data point. We'll just plot the average. But then we'll indicate how accurate and precise using these bars. So it kind of takes this. So the small standard deviation will oftentimes lead to a small error bars. Yeah?
What does that say about the paper, like, little sheet?
Formula is long. We'll use sheets. You don't have to. Formula is a pain in the booty. You can write that. You won't have to calculate it very often. We use technology to calculate it. So sheets, I was saying like use Excel or use Sheets. Okay? Whenever you do a lab that we're going to use it for after this, you're going to simply put the formula in, and that's it. You won't have to calculate it. Okay, but I wanted you to calculate it so you could get kind of practice and idea where these numbers are coming from. Deal? I'm stopping on that. No, there's another page, I know. But that is good for just the calculations part of it and an overview of it. So go ahead. We only have like 10 minutes. See if you can calculate.